Hi guys, I'm happy to share with you guys the cellular automata that Reed and I made, and it is a cellular automata that operates on a 2D grid, and you could use it to model the spread of disease on the ocean floor or basically any other 2D kind of like surface. So the question we wanted to answer is how could we model the spread of disease over some area where the appearance of disease first depends on the presence in its neighborhood, and second, if the disease could randomly flare up, making it more likely for your neighborhood to become infected. So one specific application for this we thought would be sea star wasting disease, which does great damage to ecosystems, basically in oceans all around the world where you have sea stars. It affects a number of different species of sea stars, and its cause is mostly unknown, but it probably has both microbial and environmental factors that influence its spread. It spreads really quickly. Sea stars die within days, and there's outbreaks that could spread over thousands of miles in basically under a year, where the effects could linger for a really long time. So without further ado, I'm going to get into the model itself. So this basically are our update conditions. So we do asynchronous updates. So on every round, first cells with a disease score of greater than 5 in their more neighborhood become affected, and then some proportion of those affected cells will develop severe disease on each turn. And here's how we define the initial conditions. So we have two different probabilities. First, these initial conditions are also assigned asynchronously. So first, we assign some proportion of individuals to the affected state, some proportion of the remaining individuals to the severe state, and then everybody else is basically unaffected in the beginning. So these are the basic rules of our model. And without further ado, we could start looking at the results. So here we see that the disease is quite sensitive to initial conditions. So here our P's is not the total proportion that's affected with either severe or regular disease at the beginning, but that's just equal to the score of one and the score of the other. So here you actually start with about 19% affected and so on. So here we see if you don't have enough individuals in the beginning, the disease fizzles out. If you have an intermediate number, you have the disease lingering, but not necessarily spreading very quickly. But in this high initial condition, you see the disease could spread quite quickly. So our model is quite sensitive to initial conditions. And if you change it so P1 doesn't equal P2, you can make up for less severe disease in the initial condition with just more cells affected. And you still see the same effect in terms of the rate of spread in these first 50 times that you run the model. And here is the same thing with the Q probability. So this is the chance that a given cell will turn severe in a given turn. And here you see much the same thing, where if Q is low, you don't have enough cells becoming infected, so the disease could spread, it fizzles out, or the number of cells becoming severe in a given turn, right? So the score doesn't get up high enough, the disease fizzles out. At intermediate values, the disease, like I said, could persist in just small areas, and sometimes they're larger and smaller. But if the Q, right, if the actual proportion of severe individuals gets up really high, you see that the disease can spread quite quickly, actually. So this doesn't even take the whole 50 turns. If you have 30% of your affected cells essentially becoming severe in a given turn. So the last sort of comparison I want to talk about is the actual neighbor conditions. So here we see that we're also really sensitive to that as well. So with these initial and sort of probability conditions, we see that basically no matter what you do, if it takes only 4 neighbors to cause disease, it colonizes the whole thing very quickly. But if you acquire more, you need much more strong initial conditions, more severely infected individuals or anything to spread the disease. As you could probably see here, it dies out quite quickly where you require a count of 6 and you keep these initial conditions the same. We hope that you enjoyed our model, and we look forward to sharing the code for Sunday. Thank you for listening, guys.